Back here live on PALS TV, everyone. Next, we're going to be heading to Columbus, actually down to right outside the lines, though. Our own Professor Phil is going to be joined by a very special guest today. I want to give a shout out and say a very happy birthday to Bianca. We're so fortunate to have her be a part of our team here at PALS. I've watched her do nothing but give back to others for the past several years. And, you know, it's very thankless in everything she does. We appreciate you, Bianca. You're wonderful. And loved having you on here on PALS TV and looking forward to your segment this afternoon, but a little premature, but happy birthday. Now we're going to be doing Professor Phil's segment here with a little weird science. He teaches us so much during these segments. You never know what to expect in Professor Phil's lab. Let's just hope he doesn't blow up anything today. I always worry about that in these segments, but other than that, they're a lot of fun. So sit back and enjoy. And live from AOTL, you have Professor Phil.
Welcome back, gang. I don't know that we're going to blow anything up, but let's do our best to try and do that, because that's definitely exciting. So today, we're going to be talking about electricity. And we'll be talking about magnetism a little, but that's because they're kind of the same thing. We'll get into that in a second. But the first thing we need to do today is to look at the stuff that we started last week that wasn't going to get done. You know, I'm not wearing the lab coat today. That's because electricity is not going to get on my skin in the kind of way that a fluid would. If it gets on my skin, I'll just burn, and lab coat won't really help me. So, because of what we were dealing with yesterday, we will start wearing the gloves. Because as you recall, we had started our bacteria farms, and I definitely don't want to cover my hands in bacteria. That would not be pleasant. All right. We'll bring these over. Lab technician, where do you think we should start?
Let's start with your toilet.
My
Professor
toilet.
Phil.
Okay, so let's take a look at what we found in my toilet now that it's been growing for a week. Let's see what we can see. Yeah, that's better. Okay, so we've got this white fuzzy stuff and we've got this dark green. The green is mostly the bacteria. The white fuzzy stuff is going to be some kind of mold that we probably picked up by cross-contamination. We did not do the most rigorous cleaning of our equipment and things like that, so we probably picked some stuff up. This can be a problem in any kind of science. You get stuff that you weren't expecting that fills in. That's why everybody wears the big suits when they're working on diseases and things like that. It's not so much to keep you from getting it, because you're probably not. When you work with a disease, it's usually dead already. But if you bring something in and mess up your experiment, then you're going to get bad results. And it may think we've got a cure for some disease, and we don't really have that. So we've got a fair bit of bacteria there, but most of what we get from my toilet is mold that we picked up from anywhere. It is quite thick bacteria, though. I don't think you can see that. We've probably got, at its biggest, almost a 1/16 of an inch palm. I'm leaning into this, and that's not wise. Okay, so that's my toilet. I think that after my toilet, we definitely have to go with the AOTL toilet. All right, so the AOTL toilet is almost totally green. There's not much mold in there at all. The little donut you can see right there. But there is a lot of bacteria at the AO toilet compared to mine. This may be because, again, of issues with contaminating our samples and things like that. We didn't have real Petri dishes. These are pretty good for working at home and just seeing stuff, but it's not as clean as it could be. And we've got about the same, it's a little thicker than mine. So there's quite a bit there. And you would expect that because you've got a greater variety of people using the toilet here. So more bacteria from different people are going to show up. We don't even know if these are like unhealthy bacteria. They might be perfectly fine bacteria. Okay, let's try the door. Good with the door, lab technician?
What?
The door. We did the door handle.
Yes, we did the door.
So the door handle. We're touching door handles all the time. Let's see what we find in there. Oh, that's a lot of stuff. Again, a lot of green. Well, that's all bacteria. You can hardly see it, but next to this white bit of mold here, we also have some brown bacteria. There's a wholly different type. So we've got more types of bacteria that we can see without even looking with a microscope, just on the door. So more types of bacteria that we found on a door handle than we did on the toilet. That is definitely a good reason to wash your hands when you're just walking around. You know, there's all kinds of bacteria in the places you wouldn't think it would be. And our last sample came from my mouth. So there's definitely bacteria in there. We've got all kinds of bacteria in us that help us out. And almost no mold in this. It's just a very thin line, but all green. And no brown bacteria. I got less different types of bacteria that we can see with our naked eye than a door does. That's how clean I am. So you want to make sure that you clean your mouth a lot. There's bacteria in there. A lot of it's good and helps you out, but some of it isn't and can make you sick. So you want to make sure that you clean a lot into your mouth. Brush several times a day, lots of mouthwash. And we'll get more into that next Friday when we cover dental hygiene in health class. But you'll remember last week that we tried to get an egg sucked into an Erlenmeyer flask, big triangle-looking piece of glass, and that didn't work out real well. And because of the way we deal with science, the appropriate thing to do was to smash that egg on the ground. And we saw that egg go all over the place. Regular hard-boiled egg, you smash it on the ground. But we had a second hard-boiled egg, and we've had that in vinegar for this entire week. And we had some green food coloring because it just looks sciencey. Everybody likes that kind of thing. And we're going to move outside with the camera and see what happens with this egg, particularly because it's covered in green vinegar. I don't want to throw it on the ground inside because that'll be messy. So let's go on out here and see what happens with this egg that's just been sitting in vinegar. Good time. Oh, that's hardly any rain at all. All right.
Can you see?
I can see. I'm not sure how the light. Oh yeah, that's much better. Whoa. Okay, so this thing is slippery for one, and my hard-boiled egg can just be
Whoa!
sweet. It's all rubbery. Let's see what happens when we drop it on the ground. Oh, a bouncing hard-boiled egg. Doesn't bounce very much. Yeah. And now it's all weird and flat. That's what you can do with a hard-boiled egg. We didn't do anything special to it, but the acid in the vinegar will work on the calcium on the egg, and it with all the proteins in there, and it makes a kind of glue out of everything. You can do that with chicken bones as well, because they're mostly calcium. So if you've got some of those around, you can make rubber chicken bones. and then give them to your dog just for fun. Then they won't splinter and get in their throat. I know. So let's go back in.
Back to the lab.
All right, so that's our last week. Let's get into electricity. So electricity is, whoa.
Oh, shoot. Sorry, everyone. I lost you. Here we go. Got to protect my laptop. Here we go.
That's why Bianca's title is lab technician and not best boy grip. That's the electrician, not a film set. Or electrician's assistant. So electricity. We know that atoms, the fundamental building block of everything that is, are made up of positive particles and negative particles. The very simplest atom is a hydrogen atom. That's a type of gas, the most common gas in the universe. So it's got a proton in the center, which is a positively charged particle. And around that spins one electron, which is a negatively charged particle. Those electrons, those negatively charged particles, are all that electricity is. It's those moving around. So we can get electricity from anywhere. All kinds of stuff has some sort of electricity in it because that's what makes up the universe, basically. So these negative electrons flowing out of a thing, or say battery here, well, you can't see the terminal with the cap on. We have a positive end and a negative end. And this negative end sends electrons out. If we connect it to the positive end, they will try to go there where there aren't so many electrons. And that flow of electrons is what we call electricity. So electricity doesn't exist by itself. There are four forces that make up the universe of energies. The others don't really matter right now, but so you know, it's the strong and weak nuclear forces, gravity, and then electromagnetism, because electricity and magnetism are always together. If you have an electrical current running down this wire, that creates an electrical field going this way. And always there will be a magnetic field that goes the opposite way. It will go around like this. So anytime you've got electricity, you also have magnetism. And that means we can use them together to make things and to make things happen. So if you have a regular AA battery, I accidentally showed you the brand. I was going to avoid doing that, so I didn't, give free advertising to Giant Eagle alkaline batteries. They're not just for breakfast anymore. So regular AA battery and a bit of copper wire. There you can see that. And I've got some rare earth magnets, 4 of them, little tiny ones. Yeah, there we can see. Boom, that connected. So if we take the battery and slap those magnets on the end, we will want the positive end where electricity goes to, that'll point up. The positive end on a battery is the one with the little bump on it. We've got this coil of wire. We can set this down. You got to balance these. It's very difficult. So we want the one end of the wire to touch the little bump on top and the other end to connect with the magnet. Which is not doing very well. And it will spin like this. And it will continue doing that until we run out of electricity in the battery. Yeah. I don't want to try to move this again. That may have been moved. Oh, yeah, we moved it right out. I didn't balance my spiral very well. Here we go. That just sped up a lot. Because it's not greatly balanced and I don't have a great end, this will continue to do it until it falls off of the top, which is what happened and stopped it last time. And just then again. However, our lab technician happens to be a skilled artist. So perhaps she can create one that works a little better on balance. You think you can make kind of like a heart shape?
Yeah,
That's balancy.
like a big heart. Like you want these two ends to connect.
Well, they need to touch this and the top would sit there. And that's what it would balance on.
Got it.
All right, so while she's trying that, we're going to try something else. It didn't work real well when I tried it before. But we know now that we can use this magnetic field created by this to move things. We can move that wire if we take electricity and shove it through this. However, if we take these magnets, rare earth magnets are very strong. And we put them, two of them, four of them, two on either end of the battery. And we want them to, as electricity has positive and negative ends, magnetism being the same thing, also has specific ends. So magnets can be pulled together if you put them in one direction, but if you flip them over, they will push each other apart, and I can't get these together. Yeah, sure, that'll probably work. So if I put the ends that push against each other on either end of my battery, now you're not seeing the thing. We take this coil of wire, and I hope this works. It totally doesn't work. I think that my coil is a little too big. If it was closer, what would happen is that same power that swung that around would pull, we go backwards, nope, would pull this battery through like a train. And it definitely didn't work now. But I have this great coil of wire that I have no idea what to do with. All right, you good with your balancing act? Okay, so these things are really strong. And if you have your finger between them when they smack, it really hurts. So don't do that. All right, we have our battery there.
Like, what is this supposed to? Are these supposed to hit the bottom right here?
Yeah, I think it might be too tall, so let me hold this up.
Maybe I can make these a little.
Oh, that's not gonna work. It's gonna run into my hand.
Oh, let's put it down and I
No,
can make
let's
it
see.
shorter. No, I don't want.
It's not gonna hit my hand that hard.
Oh no.
All right, see if you can tweak those in and touch that thing. Well, they're definitely touching because my hand's getting hot as the electricity runs through this thing. But we don't have the balance on this one. That's the toughest part of this demonstration. Getting the balance is really difficult. This is what we call a homopolar motor. Rather than a positive and negative, we have a north and south pole. It means the same thing for magnets. So we've got all our poles are the same. This end and this end are magnetically going to be the same. They all go in the same direction. So that is what is driving this electrical field, is the magnetic field moving along it. And I keep grabbing this thing. Where is my next thing? Okay. I'm really disappointed the train didn't work. But it would not be the Weird Science Hour if something didn't work. I'm going to demonstrate something for you that you can build at home, but I can't really show you how it works here because I don't have a good thing. This is an electrostatic detector. So you can find, no, we don't have that. You can find out if there's an electrical field someplace. All you need is a styrofoam cup, regular aluminum can, a couple bits of aluminum foil. Try not to knock them off like I just did. Well, I might as well. And you're going to tape the can to the styrofoam cup. And you will make tiny little shepherd's crooks on the aluminum foil. Oh, somebody got that. And then those are hooked on to different parts of the pop tab. And if it gets very close to something that has an electrical field, and I can do it here and I can see it moving, but you can't because by the time I get it there, it's too close to the camera. These two will pull away and point straight out. You can try this on any kind of thing. A handy one to do is put it next to your microwave, and if these pull off, you need a new microwave because it's leaking and not safe. You could also just put it up right next to a television, particularly an old television with big cathode ray tube, the big heavy ones. So that's something you can do and check out yourself. It doesn't really work here because I don't have a source of electrostatic energy. Unless you got a bunch of balloons, you want to rub them on your hair. But I know we don't have balloons here.
And Phil, my hair looks great today. So
Okay, so electricity is this basic form of energy, and we can do a lot of different things with it. We can make magnets, we can make motors. That's all this was. We can make things move. As you know, we can turn on lights. But we don't just need to use these batteries. Like I said at the beginning, electricity is just electrons moving. So there's electricity in everything that has electrons, and everything has electrons. You can get electricity from anything. One of the easiest ones is your common, humble, everyday lemon. I mean, you can do this with a potato too, but it's not nearly as good. To make the lemon battery work, you want lots and lots of juice. So your general battery is just two types of metal. One that has an extra electron that it wants to give up, and one that has fewer electrons and needs some more. And that'll make the electricity, the electrons, want to go from the one that has too many to the one that has too few. To help make those electrons go away, we use acid. So the acid will help break things apart and will create an electrical current. That's what's happening in like a big car battery or truck battery. Old batteries we used to call lead acid batteries, because that acid would react with the metals and that would cause your electrical current to flow in your battery. That is also why you don't need batteries or break them or throw them in the garbage, because they have acid in them and it's dangerous.
what do you do when you want to throw them away?
Why, you take them to the electronics recycling place.
Oh,
There is one just north of PALS, Columbus.
great to know, Professor Phil.
So I have a zinc nail and a copper nail, and they are connected with a piece of copper wire. I'm going to get a good juicy lemon. So I get lots of the acid from there, and I'm going to shove this into my lemon. And that's just not enough electricity for me. So I'm going to do it again. When you do this, you want to make sure that your copper wires do not touch each other. They have to be separate. And I'm going to do it again because, you know, still not enough electricity. Get those nice and deep in there. Get all that juice flowing. And one more time. That doesn't seem wise. You don't really need to make sure they all point the same way. But it just looks untidy if they don't. So I'm going to turn the first one I did around, put it back in the other way. So I've got all my zinc on one side, and all my copper on the other. And then I've got one zinc and one copper on two long wires. And these will be the leads that take electricity and shove them into other things. So for this next bit, we're going to head outside to see what we can do. Or do we want to go in the back? Do you think it's light? There's a little rain here, and the rain
We can go
is
to
not
the garage.
very useful. Okay, so we're going to go to the garage instead.
Like we'll open up the garage. Hey everyone, you get to stare at my face. Professor Phil, keep up with me. We have a nice awning over here.
Okay. Oh, drop my beaker. So we have our lemon battery almost in place. We have a beaker of water for safety. We're going to keep that well away from the electricity because water, everybody tells you that water conducts electricity really well. It doesn't conduct it all that well, but better than air. So we don't want to accidentally electrocute ourselves with the lemon. Here, the aluminum foil is just to keep anything from getting on the ground. We've got some bits of paper, which I'll explain in a second. And we've got some steel wool here. So steel wool is a metal, just like this copper, and those metals conduct electricity really well. Now, what happens when electricity goes through a substance is that all those electrons run in to all the electrons inside the thing, and some of them bounce off. And when they bounce off and don't go straight through, that's our electrical current going straight through, the bouncing off creates heat. Most of the time, we don't want the heat there. We try and get rid of the heat when we're working with electricity. But it does mean we can use that heat to do different things. So we'll connect one end of our lemon battery and the other end of our lemon battery. Should have brought the other battery just in case this doesn't work. And right now I am completing a circuit and the electricity is going through me, but a lemon has very little electricity. So it's not hurting me. I'm going to shove one end into the steel wool. There, got it. Thanks. I would have. Actually, yeah, hold it down now. So now I've got this other end. And I'm going to shove that in there as well. Fairly close. No, not until it starts to burn. We may not have enough electricity in this.
I feel
lemon.
heat though.
Is it heating up?
Yeah.
Get those in there.
I'm supposed to touch you.
I'm going to try and get this so it doesn't touch the ground. So you may have heard of grounding a circuit. When we talk about that, we literally mean ground. The Earth itself will get rid of electricity. It just sucks everything up because it's so big. That's what we mean by that. All right, that's starting to get warm, but not enough. So if we had a bigger lemon, or maybe a potato battery would work. But we can still do this. And I'm going to go get a device to help us. And Bianca's going to entertain you.
It's almost the weekend. Hey, guys. How's everyone doing? Good. Lauren, what are your plans for the rest of the week?
I have no idea.
Right? That's the
Honestly,
that's normal. That's the norm
I'm
now.
a little disappointed right now, but
Well, hopefully Professor Phil can cheer you up because he just came back. All right.
So rather than the lemon, we're going to use that actual battery we had before. Shove this into here.
Hi, Gila.
Okay.
What? Sparky?
So we create sparks with this heat. They're all kind of on the other side. You pop up. I'm looking down.
Okay. Like that? Can you see?
Yeah, that's probably good. I hope you can see these sparks. And if you have good tinder, instead of cheap paper. Oh, there you go. It also helps if you rub it a bit, that gets some more in there. You want action. Whoop, that's coming right out. All right, so clearly it works well enough that you can scare the lab technician. So if you have good tinder and a battery and some steel wool, you can go ahead and start a fire anywhere. Oh, that's hot. Like really hot. Not burn myself. Yeah, not pleasant.
Don't do this at home, you guys. All right?
No, do it in the woods. When you're lost and you need a fire and things are dangerous. All right. And this is quite warm. But if there's no spark, it's not actually creating heat that's going to burn you. It's just kind of warm. It doesn't really get that hot. The wire, on the other hand, gets very hot. So, avoid that one. All right, let's go back in. There are mannequins and things around here at the studio, and every time I see them, I think it's an extra person. That really scares me.
We like to keep it interesting at AOTO.
There are some other things we can do with electricity, but I'm going to guess that we probably shouldn't because they're very dangerous. But you can make art with electricity. If you have a magnetron, which is the device inside your microwave that makes it make microwaves, and you connect wires up to that and put those on a piece of wood, it will burn through the wood in this great big tree pattern. It's very exciting. It's also incredibly dangerous, and I don't recommend you do it at home, but it is a fun way to make art. And science, they always go together. Yeah, definitely don't try to draw with your microwave at home. That's something that you should have a professional with you to do. Oh, yeah. You can try the dating site Tinder to start a fire.
Every time
Meow. Oh, I'm stuck on that joke now. So there are many things you do. There's a different type of electricity that we get out of these cords that come out of our wall. What we've been doing is just driving electrons one way. If you want to do the really dangerous stuff, which you shouldn't do, you will need electricity that goes both ways. That's what comes out of your wall and through the big electrical cords. So we could snip off the end of this and get dangerous things, and that would very likely kill me. So we're not doing that. Batteries, on the other hand, are pretty safe. These are not. So when you're doing experiments with electricity, use a battery and not the house. If you try and use the house, you will probably hurt yourself. And that's why I'm not doing it. I've got the stuff to do it, no problem. I got my wire cutters, I got my wire. I could do it, but it's not safe, so I'm definitely not going to try that. Next week, we're going to be working on sound and music and all the science behind that. But for right now, let's go into some questions. What do people need to know? And any ideas you might have for future things that we could try out. Give a wave. Oh, come on, where are you guys at? You're always waving. Nothing? Oh, you're waving. No, too bad. Lauren, what do you got?
Hi.
Hi, how's it going?
Lauren is supposed to say hi to me. That's why she said
What
hi.
kind of sciencey stuff would you like or want to know about?
How to stay warm? I'm freezing.
Okay,
How
do you
to
know how to
stay
make those
warm.
hot pad, like those hand pads?
I don't know if I have the stuff, but yes, we could make, you can make, little warming pads or, what's the one that Shaq used to sell? One around your back? I love those stupid things.
Icy hot?
No, not icy hot. That's a different thing. But those are just chemicals that you crush up together. And when they react, they create what's called an exothermic reaction and produce heat. I've got several chemicals that will create an exothermic reaction, but I'm not certain they're safe. I'm gonna have to check in what's safe that I can do.
Bye, Lauren.
And Gila, you had something. What's going on, Gila?
Nothing. What's up?
Not a thing, Gila. Just trying to make it safe and get the good word so we can open and get everybody back. Because we really want everybody back as soon as possible. But we're not doing it until it's safe.
Hello.
Yes.
You ready?
Oh, sorry. No.
You ready?
Is it raining?
Oh,
Am I
go.
ready?
Yeah, I will tell you. You ready? So I have my mom was texting back you about meeting. So I go back with you.
About your meeting?
Yeah.
I,
So AOP meeting.
we've got that covered.
Scotty. Go
I'm
Scotty.
talking to your service coordinator and stuff, and it'll all be
Bill.
fine. We'll do it just like this, probably.
Bill. Scotty. Scotty.
Yeah, we'll take care of it. Don't worry.
Miss Scotty.
Gotcha. Anybody else got anything? Nope, there's Caitlin. Yes, Caitlin.
I got this history book.
Oh, that is excellent. You know what would be a good idea if everybody would like to come up with their own experiments and demonstrations, we could just all show them to each other one by one.
Okay, this is
Or at
walking.
the end of every one. Caitlin, look through that thing. Find
Walking
something
on
you want
water.
to do next week. Walking on water. That's a great idea. You know the water skimmer bug that walks on water, or a water bargeman? I don't remember what we call it here. They make an incredibly loud noise. And we're going to repeat that next week. So that'll be exciting. All right. We're all good. Gila, is this about your meeting again?
No. My mom and I was back last week because I gotta go to my car to help. Because I can't get my house because my husband helped for me.
You should have a segment on here.
Yeah.
Why?
We're going to talk to the producers. Maybe give you your own segment on PALS TV. You can host.
Next week, and my mom.
Yeah.
My egg was problem, and they help.
Oh, okay. Wait till you're back, Gila. There we go. Whoa, what happened? And we're moving the hose around just as I'm trying to move stuff. And over, there we are.
We're good. Thank you, Professor Phil. Always fascinating stuff. Those questions never get old, Gila. So thank you. Great suggestions, Lauren, Caitlin. I love those ideas. And I think that's the beauty of science, right? You can have so much fun with experimenting, trying different things out, and just we're all learning together. So thank you, Professor Phil, and your wonderful assistant, Bianca. You did great as always today. Bianca, we will see you soon. Professor Phil, we'll see you tomorrow. All
Take
right.
care.
Everyone else, come back and join us for our lunchtime segment over in Heath. So we'll be joining you in about 17 minutes. So come back and join us here soon.